What if NASA's live feed captured a glimpse of an alien probe, only to cut out at the exact moment it came into view? On June 18th, a single, baffling frame from the feed tracking our third interstellar visitor, 3I Atlas, showed something that looked unnervingly artificial. Then the screen went black. The official story is a network glitch, but the data, verified by citizen archivists worldwide, is real. So what was that razor-sharp edge glinting in the dark? Let's explore this together. The initial discovery. It all starts with a new traveler in our cosmic neighborhood. But this was no ordinary visitor. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a NASA-funded project led by principal investigator Larry Deneau at the University of Hawaii, flagged a new object. This system is our planet's frontline defense, a set of robotic telescopes scanning the entire sky every 24 hours to find asteroids on a collision course with Earth. But this object was different. Its trajectory was hyperbolic, meaning its velocity was so high it was clearly not bound by the sun's gravity. It was a perfect arc, slingshotting through our solar system on a one-way trip back to the interstellar void. Astronomers globally scrambled to confirm, and within 24 hours, the Minor Planet Center designated it 3Y Atlas, cementing its status as only the third confirmed interstellar object ever detected. The first images revealed the classic fuzzy coma and faint tail of a comet, but its speed and path told a different story. This wasn't one of ours. It was an emissary from deep space, a priceless opportunity for science. The discovery itself was a massive win, a testament to how far our detection capabilities have come since the first interstellar object, ʻOumuamua, nearly slipped past us unnoticed in 2017. The anomalous frame. Here's where a routine observation becomes a global mystery. The last recorded frame from NASA's feed, time-stamped at 03/17/12 UTC, appears normal at first. You see the dim nucleus of 3I Atlas, its hazy coma, and the faint tail streaking against the black. But then, in the lower left quadrant, something catches the light. It's a glint, but not a soft, natural one. It's a perfectly straight edge. Not a curve, not an arc, but a sharp, geometric line. This is what physicists call specular reflection. Light bouncing off a smooth surface at a definite angle, like light off a mirror. This is in stark contrast to the diffuse reflection from a rough surface like a typical comet, which scatters light in all directions. Independent astronomers, spurred on by the kinds of questions that Harvard researcher Avi Loeb has been asking with his Galileo project about potential technosignatures, ran edge detection algorithms that flagged the anomaly within hours. The software highlighted a line segment measuring roughly 37 pixels, reflecting sunlight at an angle that defied easy explanation. Comet dust scatters light in chaotic, soft ways. This was different. The light bounced cleanly, as if from polished metal, not fractured ice or rock. It was a detail so out of place that it immediately raised an unsettling question. Was this natural, or was it engineered? Data verification. Before anyone could cry cover-up, the question of authenticity had to be settled. Was the image even real? This is where the story takes a fascinating turn, thanks to a global network of citizen archivists. These individuals run automated scripts that constantly monitor and download raw public data feeds from space agencies. Within minutes of the blackout, independent archivists in Australia, Germany, and the United States had already uploaded their captured data packets to public repositories. Each file, stamped with the same 03/17/12 UTC timestamp, was secured with a unique SHA-256 checksum. Think of this as a long, unforgeable digital fingerprint for the file. If even a single bit of data were changed, the fingerprint would be completely different. When compared, every single copy matched, bit for bit. The Australian archive's hash matched the German university's mirror, and the original NASA relay. There was no evidence of tampering or digital manipulation. This airtight chain of custody proved that the anomalous frame was not a hoax. The data is real, the archive is clean, and the mystery, as the great astronomer and science communicator Carl Sagan would say, is worthy of investigation precisely because the evidence is preserved and verifiable by anyone with an internet connection. Technical explanations. So, if the data is real, could the blackout just be a perfectly timed coincidence? Here's what matters. NASA's live feeds are, well, incredibly complex. They rely on the Deep Space Network, which is this global system of massive radio antennas in Goldstone, California, Madrid, Spain, and Canberra, Australia, all working together to keep constant contact with spacecraft. This network, along with the tracking and data relay satellite system that was first launched way back in 1983, bounces signals from deep space back down to Earth. Dropouts, honestly, are not uncommon. Because the Earth rotates, a probe will eventually set below the horizon for one ground station, and the signal has to be handed off to the next station in the sequence. Sometimes this handover isn't seamless, and you get a brief interruption, what engineers call a handover blank. These usually show up as a 2-second gray screen. Each entry in the Deep Space Network logs, overseen by managers like JPL's Bradford Arnold, almost always provides a reason code like packet loss or relay outage. But the blackout at 0317 UTC, right at the exact moment the anomaly appeared, didn't fit the typical pattern. The public logs showed a gap without the standard explanatory code for a routine handover, making the timing deeply suspicious to many observers. Digital forensics. Let's zoom in on the pixels, because that's where, honestly, the technical debate gets pretty intense. Digital forensics teams immediately analyzed the last frame, and they found two key clues that could offer a mundane explanation. First, the sharp edge of the glint ran perfectly parallel to the borders of several 8x8 pixel blocks. That's a potential fingerprint of the MPEG video compression algorithm. To save bandwidth, these codecs slice frames into a grid, and can sometimes exaggerate or sharpen faint lines, snapping them into these unnaturally straight, blocky outlines. The second clue points to cosmic rays. Space is just filled with high-energy particles that can strike a camera's sensor, leaving a bright white streak that only lasts for a single frame. Digital image experts and university professors like Hani Farid have shown how these single-frame artifacts are actually pretty common in space photography. So one theory is a double hit. A fleeting cosmic ray created a faint streak that was then amplified and sharpened by the video compression, resulting in an illusion of a perfect edge. This provides a plausible, purely technical explanation, but it doesn't entirely close the case since the consistency and brightness of the glint were still considered unusual, even for a compression artifact. 3I Atlas background. To understand the anomaly, you have to understand the object itself. 3I Atlas was already a cosmic outlier before the mysterious frame even appeared. Spectroscopic analysis from the James Webb Space Telescope, detailed in papers by researchers like Martin Cordner at NASA's Goddard Space Flight Center, revealed that it was unusually rich in carbon dioxide. Most comets from our own solar system's Oort cloud, like the famous comet Hale-Bopp seen back in 1997, are primarily driven by water ice sublimating into gas. But 3I Atlas had a carbon dioxide to water ratio of nearly 8:1. This means CO2 was the main engine driving its outgassing and creating its massive coma, which stretched for hundreds of thousands of kilometers. This dense cloud of dust completely obscured the nucleus, making its exact size difficult to pin down, though estimates placed it at under a kilometer in diameter, similar to our second interstellar visitor, 2I Borisov, which was studied in 2019. The Atlas survey's ability to scan the entire sky quickly allowed astronomers to catch it early, providing a rare chance to watch an interstellar comet wake up. This unique chemical makeup already marked it as fundamentally different, a clue that it likely formed in a very different kind of star system than our own. Scientific scrutiny. In science, especially when claims are this extraordinary, the burden of proof is immense. The process of verification is honestly a gauntlet of scrutiny. An anomaly seen in a single frame by a single instrument is just the first step. This principle that extraordinary claims require extraordinary evidence is a cornerstone of the scientific method. If one observatory reports a geometric glint, others need to see the same thing, ideally across multiple wavelengths of light, to determine its material composition. Only then does the peer review process even begin. At every stage, scientists are trained to ask, is this a real signal, or is it an artifact? For 3I Atlas, the evidence so far sits on the lowest rung of this ladder. We have one intriguing frame, but no multi-instrument confirmation. Until the Hubble, Webb, or major ground-based scopes produce matching data, most researchers, including veteran SETI Institute astronomer Jill Tarter, would advocate for caution and continued observation, not immediate conclusions. It's a slow, methodical process designed to filter out wishful thinking and avoid the pitfalls of past astronomical misinterpretations, like Percival Lowell's infamous belief in the canals of Mars in the late 1800s. 3 theories. The debate has now fractured into 3 distinct paths. The first is rooted in known physics. Comets are violent, dynamic objects. As 3I Atlas neared the Sun, intense heat could have caused thermal fractures, splitting off a shard of rock or ice. Jets of carbon dioxide erupting from the surface can create torque, making the nucleus spin faster and faster until pieces break off. The glint could simply be sunlight catching the fresh, flat, crystalline face of a newly broken fragment. The second path points to a technical illusion. This is the Occam's razor answer, arguing that the edge is nothing more than a perfect storm, a chance alignment of a cosmic ray, digital compression artifacts, and background noise that tricked our eyes into seeing order in chaos. But the third idea, the one that captures the imagination, persists. This theory, in the vein of speculative ideas from physicists like the late Freeman Dyson, proposes that the edge is exactly what it looks like, something manufactured. A piece of a self-replicating von Neumann probe, a solar sail, or a protective shell designed to withstand interstellar travel. If true, it would mean we're looking at a message or a machine, not a comet. The odds are, honestly, astronomical, but the possibility lingers. Broader implications. An event like this, a potential signal followed by a sudden blackout, ripples far beyond astronomy labs. It triggers a profound shift in public consciousness and even scientific policy. The central question expands from what is that object to who controls the narrative of discovery. It fuels calls for greater transparency, with organizations like the Vera C. Rubin Observatory in Chile being designed specifically to capture and share vast amounts of data openly. For those of us watching, it becomes a powerful test of critical thinking, echoing the public's reaction to the famous 1977 WOW signal. That was a powerful 72-second radio burst detected by astronomer Jerry Amon that remains unexplained to this day. How do you separate a genuine mystery from a technical glitch or a cover-up conspiracy? The timing of the feed cut forces a conversation about our readiness for a potential discovery of this magnitude and whether international protocols like those discussed at the UN's Committee on the Peaceful Uses of Outer Space are sufficient. It blurs the line between healthy skepticism and profound wonder. If a single ambiguous frame can change how we search the skies, what happens when the next visitor leaves no room for doubt? The search continues. So, where does this leave us? The official record states that at 3:17 UTC, the NASA feed for 3I Atlas was interrupted. The final frame contained a geometric glint whose integrity has been verified. The feed drop has been attributed to routine network behavior, yet its timing remains an unnerving coincidence. As of today, there is no conclusive, peer-reviewed evidence to support an artificial origin. But the search is far from over. Missions are already being planned, like the European Space Agency's Comet Interceptor, slated for launch around 2029. It is a brilliant mission designed to lie in wait at a stable Lagrange point in space, ready to travel to a pristine, long-period comet or even a future interstellar visitor for a close-up look. This proactive approach, championed by scientists like the mission's lead, Geraint Jones, shows how seriously the scientific community is taking these objects. Every new interstellar visitor is a gift, pushing our technology, our curiosity, and our standards of proof forward. And maybe, just maybe, the next one will provide the answer we're all waiting for. The case of 3I Atlas remains a tantalizing puzzle, perfectly balanced between a mundane technical glitch and a discovery that could redefine humanity's place in the cosmos. The data is real, the anomaly is recorded, but the final explanation is still waiting out there in the dark. What do you think? Was this a ghost in the machine, a natural cosmic coincidence, or our first fleeting glimpse of technology from another star? Let us know your theory in the comments below. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our universe. Thanks for watching Future Facts.